4.2D, let's describe a completely randomized design for an experiment. Does caffeine affect the pulse rate? Example. Here, many students regularly consume caffeine to help them stay alert. Thus, it seems plausible to take caffeine might increase the student's pulse rate. Is it true? One way to investigate this is to have volunteers measure their pulse rates, drink some cola, measure their pulse rate again after 10 minutes, and calculate the increase in pulse rate. Unfortunately, if every student's pulse rate went up, we couldn't contribute this increase necessarily to the caffeine. There could be other variables out there. One of the lurking variables, perhaps the excitement of being in an experiment made their pulse rates increase. That could be the case. Another element could be perhaps it was the actual sugar in the soda and not the caffeine. There could be confounding between those two variables. Or lastly, maybe perhaps the teacher told them a funny joke during the 10-minute time period and it made their pulse rate go up. We have to control for these things. So the key here is that a good design is essential for effective experiments. We need to control for potential lurking variables. The one thing we're going to talk about is a randomized comparative experiment, and I want to break that down. We have the word randomized, we have the word comparative, and we have experiment. Each of these three words mean something very specific. The randomized part is incredibly important in that it takes care of bias. When you randomly pick your people, you do the correct SRS to it, you're going to eliminate that bias that could happen. The comparative component is important in that it prevents lurking variables to become confounding. We're going to design it in such a way that we can control for the lurking variables. In this soda case, if we're analyzing caffeine, if we want to control for sugar, how do we make it comparative? Maybe we compare Coke versus Diet Coke or caffeine-free versus regular Coke to look at the caffeine aspect of it. And then the experiment component is that a treatment is imposed. And in this case, the treatment is the soda. So the comparative part is really where you come and you think about how to design your experiment well to control, again, for the sugar, the caffeine, and those elements in your experiment. Now, the first thing you want to do in designing an experiment well is really think about that randomness. It must be that the experimental units are assigned to treatments at a random point through some sort of chance process. There's a variety of ways you can talk about this randomness in your experiment design. We have the random number generator. We have table D. The most common and the most easiest to use is actually putting slips of paper in a hat and drawing from them to create random assignment of treatments to your subjects. So let's think back about the caffeine example we just talked about. Suppose we have a class of 30 students who volunteer to be subjects in the caffeine experiment. Explain how you would randomly assign 15 students to 2 treatments, where treatment 1 is you drink caffeinated soda, treatment 2 you drink decaf soda. I'm going to show you 3 different ways to explain this. Again, the most common is going to be with paper, but if you say it properly on a free response, you could use either method for the explanation. So with paper, the best way to approach this is to say this. Is using 30 identical slips of paper, write A on 15 and B on the other. Mix them thoroughly in a hat and give each student to select one piece of paper. Have each student who received an A drink the cola with caffeine, and each student who received a B to drink the cola without the caffeine. This is a perfect way to explain making your random samples. Okay. What if I wanted to do it with table D? Fine. That approach, you could say, label the subjects 01 to 30. Go to a line in table D, read 2-digit groups from 00 to 30 until 15 are picked. Have those first 15 get treatment 1, and everyone else then will get the treatment 2. So treatment 1 could be the with caffeine and without caffeine. You have to say ignore your repeats in this because it could happen. Okay, fine. What if we wanted to talk about how to do this with the calculator? So with the calculator, I could say, let's give the subjects numbers 1 through 30 in alphabetical order by last name. Maybe that's how I want to do it. Use random integer in the calculator to produce 15 numbers from 1 through 30. The first 15 get treatment 1, the rest get treatment 2. I do want to say ignore repeats in case they do show up. Be very cautious. Remember, Chapter 4 is 15% of the actual AP exam. The most common things the AP board will find is that students fail to adequately describe how they assign the treatments to experimental units. The method must be random, and you have to describe it in detail. Let's talk about how do you set up the completely randomized design. The first thing you want to do is have the treatments get assigned to all of the experimental units, and it should be completely done in a random fashion. Now I'm going to show you, this is a really nice way to lay out how you would show the randomized design. And the AP board really doesn't mind this diagram. They actually kind of like it versus the words. In this case, we have a scenario. We have 50 volunteers. We're going to do a random assignment, and we would talk about what that random assignment is. How did we do it? Once we randomly assign them, we would say into group 1 and group 2. And here we have 25 students. In this case, they're going to be having students take an online prep course for SATs versus a classroom prep course, so that's the treatment. They want to know at the end, did the online versus the classroom actually make a difference in their SAT scores? So the treatment is really the learning method of SAT prep, and the response they're looking at is the SAT scores as they compare them. Now let's actually go back to how they created the random assignment of the two groups. Let's say that they went into all 50 volunteers, gave them numbers from 0, 1 to 50, assigned everyone a number, put the numbers in a hat, and they said the first 25 numbers that they pick, whatever they are group 1, the last 25 numbers are group 2. So we draw it from a hat. Does using this chance process to assign the treatments in an experiment guarantee completely randomized design? In this case, no, it doesn't guarantee it's completely randomized. It's a good method, but what if we did a different method other than putting numbers in a hat and drawing to see who goes into which group? So if you look at that SAT prep course experiment involving the 50 students, another way to randomly assign the subjects to the two treatments is by tossing a coin, okay? So what if we toss a coin and we say, have each student come forward and toss a coin? If it's heads, the students will get the online course. If it's tails, the students will get the classroom course. As long as all 50 students toss the coin, this is still a completely randomized design. It's actually okay. Of the course, the two experimental groups are unlikely to contain 50 students each due to chance variation of the coin. Maybe you're going to have 26 in one, 24 in the other, or 27 and 23, because the coin is not going to give you 50-50 heads and tails every single time. So here's the issue if you do the coin, and this is not a good method to actually use to explain, even though it does create a randomness. The problem is this. It comes if we try to force two groups to have equal sizes. Suppose we let the coin toss until one group has 25 students. Then place the remaining students in the other group. If you do this, means not everyone flipped the coin. So this is not a completely randomized design because the last few students aren't being assigned to one treatment by chance. They're basically the leftovers. They don't flip the coin by chance. They just go into the remaining group. These students will all end up in the same group. And this could lead to bias if these individuals share some characteristic. Maybe the reason they're lined up in the 50 students, the last 5 overslept and came in late, so they weren't prepared. The last 5 students are really similar in that they don't plan ahead, they procrastinate, maybe they oversleep. So if they don't get a chance to flip the coin, it can be biased because those not as good students might all be in the same course. So if you use the coin method, it is okay if the groups aren't equally balanced because odds are it's not going to happen. This issue method listed here is something to be cautious of, and do not use this method. Again, the AP board's going to say, careful, they wanted me to highlight that coin method for you because people will say that one, which is what we just talked about. It said on page 238, The coin method isn't really good. Use the hat method. It's the most simple way to do it and not screw things up. Let me show you how to explain to the AP board a complete randomized experiment and get full credit. Here we have dueling diets. A health organization wants to know if low carb or low fat diet is more effective for long-term weight loss. The organization decides to conduct an experiment to compare these two diet programs with a control group that is only provided with a brochure about healthy eating. So we have a control group, we have low carb, and we have low fat. We have 90 volunteers in total that agree to participate in the study for 1 year. Outline a completely randomized design for this experiment. Write a few sentences to describe how you would implement your design. Here they want you to do a diagram, and I'm going to just highly recommend that you do a diagram. I think it's easier for students and you tend to do it better. So what I would do for the diagram is first say this. We're going to do random assignment. We have 3 different groups. So we're going to, on the diagram, randomly assign group 1, 2, and 3 with 30 subjects each. Each group will then be assigned a treatment, either low carb, low fat, or the control group. Then at the end, we're going to compare those results. This is a really good way to break out the randomized design. Now let's put some words to it. To implement the design, use 90 equally sized slips of paper. Label 30 of the slips 1, 30 of the slips 2, and 30 of the slips 3. Mix them up in a hat and have each subject draw a number without looking. The number each subject chooses will be the group he or she is assigned to. I could also say on here, then randomly assign, then we could say group 1 is going to get low carb, group 2 would get low fat, group 3 would get the control group. At the end of the year, the amount of weight loss will be recorded for each subject, and the mean weight loss will be compared for the 3 treatments. Folks, one thing you have to be really cautious of, you must talk about how you're going to look at the results at the end. So the response variable. We're going to compare the response variable. People will tend to forget to mention this in their design, but it is incredibly important you talk about this last component on how it's going to be done.